In the previous classes we have been discussing about oblique shock waves and expansion waves, their analysis and their use for finding out pressure over bodies in supersonic flow, as well as what happens when these waves interact with walls or free pressure boundaries, so constant pressure boundaries. So the concepts we have covered, one elaborate numerical we have done. Now let us do a few numericals so that the application of these concepts is clear. Take numerical example 1. A uniform supersonic airflow at Mach 2.0 passes over a wedge. So you can draw the wedge. So as a wedge, Mach 2 flow is passing over it, 2.0. An oblique shock making an angle 40 degree with the flow direction remains attached to the wedge. So what is given is the oblique shock angle, beta is given 40 degrees, remains attached if the free stream pressure and temperature P1 is 0.5 10 power 5 and T1 is 273 Kelvin Pascal. Determine pressure and temperature behind the shock wave, Mach number of the flow passing over the wedge, and the wedge angle. So what is theta? Also calculate the maximum deflection angle at which oblique shock remains attached to the wedge. So wedge is usually a symmetric profile, so you have both thetas, and so it is symmetric about this line. So this is the wave feature that is given. So let us do this problem. So Mach number and oblique shock angle is given 2.0 and beta is given as 40 degrees. So theta can be calculated directly here. You can use the m theta beta direct relations directly. Because m theta beta is tan theta is a function of beta, Mach number and gamma. All of them are known, beta is known, Mach number is known, gamma is known. So theta can be found out. The theta you find here will be half angle, the semi half angle. So the wedge angle is actually 2 theta, and the wedge angle turns out to be 21.24 degrees. So directly by looking at the charts you can find this out. Okay. Since beta is given, now we have to look at what is the pressure temperature after the shock. So the way to go about this is look at the normal component of the shock. So Mn1 is m1 sin beta. This is the Mach number is 2.0. So 2.0 multiplied by sin 40. So Mn1 is 1.2855. Then use normal shock relations for the normal component of the shock. That is how oblique shock problems are solved. So for Mach number of 1.2855 use normal shock relations for Mn1. You can use a table or you can use a calculator and get P2 by P1 is 1.76, T2 by T1 is 1.1817 and Mn2 is 0.7934. So P2 is P1 multiplied by 1.76. It turns out to be 0.88 10 power 5, while T2 is T1 multiplied by 1.1817, which is 22.6 Kelvin. Okay. Now we need M2. M2 is Mn2 by sine beta minus theta. This directly from the velocity triangles. So we can get M2 here. So beta is 40 degree, theta is 10.62 degree. So this turns out to be 0.7934 by sine of 40 minus 10.62. This is 1.61. So you can see this is a weak shock in Mach 2, and the flow remains supersonic after the shock. Now the last question is, what is the maximum deflection angle at which flow remains attached to the wedge? So this again you can look at the M theta beta charts tables, and you can look at the chart, the graph of M theta beta, and find out the maximum angle. So it would be an angle like so. It's a so this is the maximum angle, theta max. So this has to be read out for a particular Mach number. So for the Mach number of 2, this theta max is close to 23 degrees. Okay. So this is how you can solve this particular problem. It's a direct problem on oblique shock waves over wedges. Now let us look at the next numerical example. A steady supersonic flow expands from Mach number m1 equal to 2.0 and pressure P1 to pressure P2 equal to P1 by P2. So there is, it's an expansion fan, and whenever there is an flow passes through an expansion fan, pressure decreases. So that is evident here. P2 is P1 by 2 from centered rarefaction. So you have a centered expansion fan, you have all these various expansion fans. So it's an isentropic process. M1 is 2.0. After expansion it undertakes an expansion to an angle theta. M2 is should be greater than M1. So now what we find Mach number and flow direction. What do we know? We know P2 by P1. So P2 by P1 is 1 by 2 or equal to 0.5. Okay, so we know this value. The main idea here is flow through an expansion fan is isentropic. So if you know P2 by P1, you can calculate the Mach number. The idea, the steps are straightforward here. P2 by P1 can be written as P2 by P02 multiplied by P02 by P1. Across an expansion fan, the flow is isentropic, therefore P02 equal to P01. Therefore this is P2 by P02 multiplied by P01 by P1, this is equal to 0.5. So P2 by P02 is equal to 0.5 multiplied by P1 by P01, and P1 by P01 can be found out for the Mach number equal to 2 isentropic charts, M1 equal to 2.0, P0 by P is 7.824. So you get this as 0.5 by 7.824, 0.0639, and corresponding Mach number for P2 by P02, M2 is 2.444. So you can approximately 2.44. So you get the Mach number. So now that you know Mach number, how do you find theta? Theta, so nu2 is nu1 plus delta theta, or in this terminology it is nu1 plus theta. So theta is nu2 minus nu1. Find the Prandtl-Meyer angles. These are again given in charts, tables, or use a calculator. So this is 37.708 minus 26.380. This is 11.328. So this is the deflection angle. So the flow is deflected away from M1 by 11.328 degrees. Okay, so this is a problem on expansion fan. So here the interesting fact was the pressure ratio was given, and from there, knowing the upstream Mach number, we have calculated all other parameters. So again you need two parameters to solve either oblique shock or expansion fan. So they can be a combination of any two parameters, upstream Mach number, pressure ratio, or Mach number and the angle. So these are the various various combinations. You can always work out different problems with different combinations of these parameters. Now we look at a problem on oblique shock reflection. We had an elaborate discussion on various kinds of reflection. There were regular reflection, Mach reflection. Mach reflection is a form of irregular reflection, but calculating irregular reflections are quite involved, and normally one uses numerical methods to calculate them, or graphical means like using a shock polar. But regular reflection can be done on paper. So we can do a problem on regular reflection. Consider a oblique shock generated at a compression corner with a deflection angle 18.2 degrees. So compression corner is a corner on which the wall has just turned into itself. So deflection angle is given 18.2 degrees, that is theta, and a straight horizontal wall is present above the corner. So above this corner there is a straight horizontal wall. The upstream flow is M1 is 3.2, P1 is 1 atmosphere, and T1 is 288 Kelvin. And what's given, calculate Mach number, pressure, temperature after reflection. So what happens here, you get because it's a compression corner and there is a turn of the flow into itself, a shock wave is formed. This shock wave impinges on the wall which is present above, and after impingement the flow has to turn in such a way that it is parallel to the top wall. So, after the compression corner the flow would have turned parallel to the compression corner. Now, at the wall the flow will turn parallel to the wall. So, the wall behaves like another wedge for the flow in region. So, if this is region 1, this is region 2 and this is region 3. So, we are required to calculate properties in region 3. So, we progress from region 1 to region 2, region 2 to region 3. So, from region 1, so region 1 to 2. So, what is given? M1 is given 3.2, theta is given 18.2, P1 is 1 atmosphere, T1 is 288 Kelvin. Knowing these parameters, we can calculate region 2. We know m and theta. If m and theta are known, beta is can be found out. Use a chart or a calculator. So, beta turns out to be 34.29 degrees. Okay. So, once you know beta, then way to go about oblique shocks is calculate m and 1 normal component of the oblique shock to the oblique shock. So, m and 1 is 3.2 sine of 34.29 this is 1.8. So, now calculate P2 by P1. P2 by P1 is 3.625 and T2 by T1 is 1.533. Therefore, you get P2 is P1 multiplied by P2 by P1. This turns out to be, since you started with 1 atmosphere, 3.625 atmospheres, and T2 is T1 multiplied by T2 by T1. It is 441.5 Kelvin. Okay. Now, we need M2. So, Mn2 is for 1.8, Mn2 is 0.6165. So, M2 is Mn2 by sine beta minus theta. Substitute the values and you get M2 is 2.22. Okay, so we know the properties at region 2. So, these are all properties at region 2. Now, we go from region 2 to region 3. From region 2 to region 3 when we go. So, we have let us remember the diagram. So, the shock is coming here and the flow is deflected and it meets this wall. The deflected flow meets the wall and another shock is formed such that after the shock the flow turns parallel to the wall. So, the flow angle that it turns by is the same as it got deflected, that is 18.2 degrees. So, this is the reference line now, this is theta, while this angle is beta. So, but Mach number now is M2, M2 is 2.22, theta is 18.2. So, for this beta is 45.36. Calculate Mn1, or rather it should be Mn2 because it is in the region 2. Mn2 is M2 sine 1.569 for this you get P3 by P2 is 2.7. So P3 is 9.7875 atmospheres, while T3 by T2 is 1.361, which means T3 is 600.88 Kelvin, and N3 is the downstream Mach number after the normal shock for 1.569. It is 0.68. So M3 is Mn3 by sine beta 2 minus theta 2, which turns out to be 1.4896. So you see that Mach number keeps reducing, pressure and temperature keep increasing after each shock, after the flow passes through each shock. An angle that the reflected shock makes with the upper wall, what is that angle? It is this angle, which is beta minus theta, beta 2 minus theta 2. So beta 2 minus theta 2 is 27.16 degrees. So here we solved a numerical example for an oblique shock reflection. So you should understand that solving shock reflections involves solving oblique shocks for each region, and it is not as simple as it is for say reflection of light, where you just do theta 1 equal to theta 2. Angle of reflection is angle of equal to angle of incidence. So it is not that, don't get confused. For shock wave reflection you have to calculate the oblique shock relations for each region as the oblique shock reflects, and after the reflection the flow will become parallel to the wall. So in this case the wall was horizontal. You could have walls at angles, so there are various combinations of parameters here also, and different such applications can arise. So with this we have covered extensively on oblique shock waves and expansion waves. So all through the discussions for a while now we have been concentrating on specific flow features. They may be normal shock waves or oblique shock waves or expansion waves. So they are all flow features that can be found in a flow. Now we move on from this point towards applications of gas dynamic principles to certain devices like nozzles, diffusers. They are a class of flows where there is a change in area. So the area changes as the flow happens within a duct. How do we solve such problems or understand in simple terms how these devices behave? What does area change do to a compressible flow? That is the theme of the next module. We will begin starting the next module with varying area ducts.